TAE supercomputing is deeply seated in history. John Dawson, then my boss, traveled to Livermore to form National Energy Research Supercomputing Center. Years later, he also collected national team to form numerical tokamaks. TAE's Numerical FRC is steeped in this tradition. We are proud that TAE supercomputing on Numerical FRC pushes the envelope of ECP. TAE has also benefited from the visit of Secretary of Energy Rick Perry in May 2019, which helped initiate the PPP.
At TAE Technologies, we're deeply involved in short-term and long-term energy research. This visualization shows our latest experiment with the plasma shown in pink and neutral beam injection shown in blue. This whole plasma object is held in place by magnetic fields, and it reaches temperatures hotter than the core of the sun. We can derive equations to describe these plasmas, but the equations are so complex that they can only be solved using massive computing resources. Simulation then becomes a discovery science, where numerical experiments are performed on supercomputers to discover the predictions of theory. This type of research is a grand challenge problem and can best be accomplished by public-private partnership. TAE Technologies brings the agility and financial resources of the private sector, and the DOE brings decades of technical expertise and supercomputing resources from the public sector. Following this approach, we have been using DOE supercomputers and working with DOE scientists to perform numerical experiments on macroscopic plasma self-organization. In this simulation, we see the plasma rearranging itself in 3 dimensions to find a more energetically favorable state. These studies will enable us to find improved operating conditions for our experiments and to design improved control technologies. Fusion plasma research has always been a driving force in the requirement for supercomputing resources in the DOE national labs. The Numerical Tokamak project was a collaboration between many national labs which got together and did the research which laid the foundation for modern simulation of plasmas. Our own simulation of transport in plasmas derives from the breakthroughs which were made by the Numerical Tokamak project. The simulation that you see here would take 10 years to run on a personal computer, but it was able to run in just a few hours on a DOE supercomputer. Our next goal is to perform predictive simulations to help us design our next step experimental device. This will require at least 10 times as many computing resources as we are currently using. To achieve this, we need to continue to partner with the DOE and the leadership computing facilities. And eventually, we will need exascale computing resources to run these models at scale.